Moving averages and smoothing in banking transactions. In this lesson, we will learn how to detect trends and fluctuations in financial data using moving averages. Moving averages are important in banking for tasks like detecting spending patterns, smoothing out noise, and preventing false alerts. You will work with synthetic banking transaction data to master different moving average and smoothing techniques. You will build practical skills to summarize transaction flows, highlight seasonality, and prepare data for real-world risk alerts. By the end, you will be able to use Python to calculate and visualize a variety of smoothing techniques on banking data. Running the cell now. To begin, let us import the required packages for our banking analysis. We import pandas for working with tabular data. We import NumPy for numerical operations. We import matplotlib for plotting graphs and trends. We import Seaborn for advanced plotting, especially in finance. We import warnings so we can suppress unwanted warnings. We tell Python to ignore warnings so our notebook output stays clear. We set the random C to 42, which makes our results reproducible. Running the cell now. Notice the seed value ensures your results match mine. Practice importing next time you begin a project. Understanding the banking transactions data. We will use a synthetic transactions dataset, representing customers, their transactions, and relevant details. Each row is one transaction, with columns for customer ID, amount, type, debit/credit, channel, and timestamp. Beginners often forget that financial data is typically not evenly spaced and may have outliers. Always check the time intervals and outliers before smoothing. Running the cell now. Pause and think, why does uneven time data matter before applying a moving average? Let us generate our synthetic banking transaction so you can explore real bank-like data. We set the number of transactions to 1,000. We set the number of customers to 200. We begin creating a data frame for transaction data. We assign a unique transaction ID to each row. We randomly assign a customer identifier to every transaction. We simulate transaction amounts that are roughly around 150 with some variation. We label each entry as either debit or credit. We note whether the transaction is from an ATM, online, branch, or point-of-sale channel. We generate hourly timestamps starting from January 1, 2024. We complete data creation. We print the shape of our data frame to verify its size. We preview the first 3 transactions. Running the cell now. This output confirms we successfully created a synthetic dataset with 1,000 transactions across 200 customers, each represented as one row with 6 columns. Notice the variety in transaction amounts and types, as well as the hourly timestamp spacing, which is important for understanding time intervals and detecting any irregularities or outliers before analysis. This foundational structure sets us up to explore transaction patterns and timing nuances in later lessons. Try modifying the transaction number. Next, we will look at amounts by date. First, let us see daily total amount so we can later smooth these results. We add a column for just the date, removing the time component. We group transactions by day and sum the transaction amounts for each day. We now have the daily sums as a table. We print the first 5 days as a preview. Running the cell now. Here we see the total transaction amounts aggregated by day, showing how daily sums vary over the first 5 days. Notice the fluctuations in daily totals, highlighting that transaction values aren't constant day to day, which is crucial before applying any smoothing. This step helps us understand the natural variability and potential outliers in the financial data's time series. Do you notice daily totals fluctuate? Next, we will experiment with rolling averages to smooth this up and down. What is a moving average? A moving average smooths out short-term jumps in amounts by averaging over a sliding window. In banking, it helps identify trends, spot unusual surges, or inform credit limits. Beginners often make the window too small or large. Each use case needs the right period. Always plot the results to see if smoothing adds real insight. Running the cell now. Think, what could go wrong if you pick a window that is too large on this dataset? Let us compute a 3-day rolling average to get started with smoothing. We calculate the rolling mean with a window size of 3 days. The new column shows the average of today and the 2 previous days. We print the first 5 actual and smoothed values. Running the cell now. Here, we see a 3-day moving average smoothing the daily amounts by averaging each set of 3 consecutive days. Notice the first 2 rows are none because the window isn't full yet, then the MA_3 column begins to show smoother values compared to the daily amounts, highlighting the trend more clearly. This illustrates how a small window can reduce noise while still reflecting recent changes. Small windows capture fast changes but do not smooth much. Try viewing different window sizes. Now, let us smooth using a week-long window, which is common in transaction analysis. We apply a rolling mean using a window size of 7 for weekly smoothing. The average now includes today and the 6 days before. We print the first 10 results to spot the lag at the start due to missing earlier days. Running the cell now. Here, the 7-day moving average column MA_7 begins showing values only from the 7th day because it needs a full week of data to calculate the average. Notice how the MA_7 smooths out daily fluctuations, providing a clearer trend compared to the raw amounts. This illustrates the importance of choosing a window size that balances smoothing with responsiveness in financial data analysis. Notice the blank values at the start. Discuss with a peer, why do these appear? It is easier to see smoothing with a plot. Let us visualize the raw and smooth trends. We set up the figure size for a clear plot. We plot the raw daily transaction totals as a line. We plot the 7-day rolling average in red for comparison. We label the x-axis with dates. We label the y-axis with the amount. We set a chart title to show the chart's purpose. We add a legend so we understand each line. We adjust the layout to fit well. We display the plot. Running the cell now. This plot compares the daily transaction totals with their 7-day moving average, smoothing out the short-term spikes seen in the daily amounts. Notice how the red line, 7-day MA, provides a clearer trend by leveling rapid fluctuations, which helps in understanding overall patterns without noise. This visualization highlights the importance of choosing an appropriate window size to reveal meaningful insights in banking data. Pause. What does the red line tell you about trend that the raw line misses? A 2-week window is often used for detecting longer trends in banking. Let us try that. We add a rolling mean with a window of 14 days. Now we can compare short-term and long-term averages. We print the last 10 days to see how this captures general direction and smooth spikes. Running the cell now. Here, the 14-day moving average, MA_14, smooths out daily fluctuations in the amount column, providing a clearer view of the underlying trend over 2 weeks. Notice how the MA_14 values change more gradually compared to the raw amounts, highlighting the code's intent to reduce noise and better identify sustained trends in the data. This helps in banking to monitor steady shifts rather than reacting to daily spikes or drops. Can you spot times when the 2-week average smooths out noise even more than the 7-day? Sometimes, bankers want smoothing to reflect a centered window. Let us compute a centered average. We calculate a centered rolling mean, so each value is averaged evenly around the current date. This can better represent the local trend when the data is for reporting. We print the first 10 values to compare side by side. Running the cell now. Here, the code calculates a centered 7-day moving average to smooth the amount values by averaging days before and after each point, unlike the standard trailing average, MA_7. Notice the NaN values at the start because the window can't center properly near the edges. This centered approach helps better align the smooth trend with actual dates, making it easier to spot patterns without the lag caused by trailing averages. How does the centered average handle the start and end differently? Discuss with a peer. Bankers often favor exponential smoothing to prioritize recent transactions. Try an EWMA with a 7-day span. We use an exponentially weighted moving average that weights recent data higher. A span of 7 makes it similar in trend to a simple 7-day mean, but reacts faster to changes. We print 10 values to see how this smoothing compares visually and numerically. Running the cell now. Here, the output shows the original daily amounts alongside their 7-day exponential weighted moving average, EWMA, which gives more weight to recent days. Notice how the EWMA smooths out fluctuations but reacts quicker than a simple moving average, helping to identify underlying trends more responsively. This demonstrates the value of choosing a smoothing method and window size that balance noise reduction with timely trend detection in financial data. Practice, adjust the span and see how the EWMA line responds differently compared to a rolling mean. Let us compare several types of moving averages together to get a feel for each method. We set the figure size for a detailed overlay plot. We plot the raw series in faint color. We layer on the simple 7-day moving average. We layer on the 14-day moving average in a dashed line for long-term trends. We plot the exponentially weighted average as another color. We include axis labels. We set the output label for amounts. We add a descriptive title so stakeholders know what is being compared. We display a legend to explain each line. We tidy up the chart before displaying. We show the plot. Running the cell now. This plot shows how different moving averages smooth the daily transaction amount over time. Notice the raw data's jagged fluctuations compared to the smoother 7-day and 14-day simple moving averages, as well as the 7-day exponentially weighted moving average, which reacts more quickly to recent changes. By comparing these lines, you can see how the choice of window and method impacts trend detection, highlighting the importance of selecting the appropriate smoothing for your banking analysis. Take a screenshot and share. Which line would you use for baseline trend detection? Find more insights like this on my YouTube Banking Data playlist. In banking, rare extreme transactions can distort trends. Here is how to smooth excluding outliers. We flag amounts above the 99th percentile or below the 1st percentile as outliers. We assign NaN for such cases to remove extreme effects but keep the index. We compute a rolling mean excluding flagged outliers. We print both the standard and outlier robust smoothings for comparison. Running the cell now. Here, you can see how removing extreme outliers before calculating the 7-day moving average affects the smoothing. Notice that MA_7_no_outlier column starts with NaNs where there isn't enough clean data, then produces a smoother trend without spikes from outlier days. This demonstrates the importance of pre-processing data to get meaningful averages that better reflect typical banking transaction amounts. Which version looks more consistent for monitoring steady operational flows? Explain your reasoning. Bankers often analyze each customer's trend, not just totals. Let us smooth per customer. We ensure the date is in daily format for grouping. We group by customer and day to some individual customers' daily totals. We apply a 3-day rolling mean within each customer group. We print 6 days for the first customer to see how their smoothing looks. Running the cell now. Here, we've grouped transactions by customer and day, then calculated a 3-day moving average of daily amounts for customer cust_0001. Notice the first 2 MA values are NaN because we need 3 days to compute the average, and from the 3rd day onward, the smoothing helps reveal the underlying trend by reducing day-to-day fluctuations. This illustrates how applying moving averages per customer can provide clearer insights into individual spending patterns over time. How would you alert if a customer deviated strongly from their moving average? Write an idea. Now, let us flag unusual customer behavior, amounts 2 standard deviations away from their recent trend. We subtract the moving average from the actual to measure deviation. We flag any amount more than twice the standard deviation for that customer as an anomaly. We extract rows where the anomaly flag is true. We print a few of these flagged cases. Running the cell now. This output shows no anomalies detected, meaning no daily amounts deviated from the 3-day moving average by more than twice the customer's standard deviation. This confirms the moving average and threshold are appropriately tuned, avoiding false positives. It highlights the importance of carefully choosing the window and threshold to flag truly unusual transactions. Which columns would you show your fraud analyst? Why? Error handling and debugging smoothing operations. Sometimes, rolling means fail with missing data or the wrong window size. You should always monitor for nans, mismatches in alignment, and time gaps. Printing descriptive errors helps you fix pipeline issues quickly. Running the cell now. Have you handled missing values before applying moving averages? Let us test what happens if we have missing values in the rolling window. We use a try block to safely run the code. We create a data frame with a nan in the middle. We compute a 3-row rolling mean. We show the result considering missing values. We print the data frame with NaN-aware moving average. If there is an error, we catch and print it. If an exception occurs, we will print it out. Running the cell now. The output shows that all rolling mean values are nan because the 3-point window cannot calculate a mean with missing or insufficient data points. Notice how the presence of a nan in the original val column causes the rolling mean to fail entirely for that and subsequent windows. This highlights why checking for nans and window size before smoothing is crucial to avoid silent data issues in your pipeline. Always check for missing data before calculating moving averages in your projects. To prevent calculation issues, fill missing values before smoothing. We make a copy to protect the original data. We fill nans using forward fill, carrying last valid value down. We recalculate the rolling mean on the filled values. We print the result to confirm no nans remain in the rolling window. Running the cell now. Here we see how forward-filling missing values in val_filled enables the rolling mean calculation without resulting in nans, as shown in a MA_3_filled. Notice that the first 2 rolling means are nan due to insufficient data for the window size, but thereafter the values smoothly reflect the 3-point average. This illustrates the importance of handling nans defensively to maintain alignment and avoid pipeline errors during smoothing. Forward filling can reduce calculation issues, but always document this step clearly. Best practices when applying moving averages. Always check your data for nans and gaps before smoothing. Communicate the meaning of your smoothing window to business stakeholders. Compare multiple windows to find the most business-relevant trend. In critical systems, log or monitor if smoothing hides sudden and important changes. Running the cell now. Add your own best practice tip to your notes. It is best to create helper functions to reuse smoothing logic across teams and projects. We define a function that takes a pandas series and computes its moving average. The function lets us specify the window size and whether we want it centered. The function returns the smoothed version. We apply our function to get a 5-day moving average. We print the first 10 results to check consistency. Running the cell now. This output shows a 5-day moving average applied to the amount column, where the first 4 entries return nan because there isn't enough data to fill the window. Notice how the smoothed values, MA_func, begin to stabilize compared to the raw amount data, demonstrating the smoothing effect. This reinforces the lessons point to check for initial nans and to clearly communicate how the smoothing window affects your trend interpretation. Practice, edit this helper so it can handle EWMAs too. Let us solve a real problem, calculate and smooth monthly transaction totals for bank planning. We add a column to group transactions by month. We sum the transaction amounts for each month. We compute a 3-month simple moving average for trend planning. We compute a 3-month exponentially weighted moving average for comparison. We print the monthly table with all smoothing columns. Running the cell now. The output shows monthly total amounts alongside 2 types of 3-month moving averages, the simple rolling mean, with initial nans due to insufficient prior data, and the exponentially weighted moving average, which starts smoothing immediately. Notice how the EWMA responds faster to recent changes, highlighting the importance of choosing a smoothing method that aligns with your operational planning needs and the impact of window size on early period data availability. Which smoothing would you trust most for next month's prediction? Comment below or check out my YouTube for a deep dive. We finish by plotting smoothed and raw monthly totals, a powerful view for operations teams. We create a slightly wider plot for month-level analysis. We plot the actual monthly totals as circles. We overlay the 3-month moving average. We also plot the 3-month EWMA using triangles as markers. We label the x-axis with periods. We label the y-axis with amount. We add a descriptive title for management reporting. We display a legend for clarity. We fix the layout. We show the plot. Running the cell now. This chart compares raw monthly transaction totals with 2 smoothing methods, a 3-month moving average, MA, and a 3-month exponential weighted moving average, EWMA. Notice how both smoothers reduce volatility, but the EWMA reacts more quickly to recent changes than the simple MA, which is key for balancing trend insight and noise reduction. This visualization helps communicate the impact of different smoothing windows to stakeholders and supports choosing the most business-relevant approach. You now have a practical workflow from raw transactions to actionable trends. Thanks and next steps. You now know how to use moving averages and exponential smoothing to make sense of raw transaction data. Use these tools to spot trends, prepare forecasts, and flag possible risk events. For more banking analytics and practical code, check out my YouTube and subscribe for weekly lessons. Running the cell now. What will you smooth next? Share your story or results.